Welcome, everybody. The speaker of our colloquium today is Petra Schwer, and she will talk about buildings, galleries, and beyond. Please.
That's correct. Thank you. Thanks a lot for the introduction. Also, thanks for having this opportunity here to tell you about my work and stuff around it. Before we get to buildings, galleries, and the other interesting things, let me start with the linear algebra problem, okay? So look at SL2 over the reals and take an element in here. And as you all know, we can decompose this group as a product of three subgroups, U, T, and K, where U is unipotent things. And if we're in SL2, this is just one entry down here, one's on the diagonal. T is diagonal matrices. So for us, this is just lambda inverse, since we're in SL2. And I want to assume that the lambda is positive to make this decomposition unique for the G. And then the K, what remains is orthogonal matrices here. So A, let's say transpose. And then we can write every such G as little u, little t times little k, okay? And the question I would like to ask is, what happens if we multiply with k on the wrong side, namely on the left, to the diagonal part, okay? So how do the eigenvalues change if we multiply by k on the wrong side? In other words, I want to determine what the t parts of elements in the right coset of k is fixing a little t, okay? So multiplying with the k on the right-hand side won't change the t part, obviously, and also does not multiplying on the left-hand side with some.
What does it say? What is, and then?
It's the projection onto t of capital K times t. And by this, I just mean all the t primes where in t that appear as a t where we have multiplied a t prime, where we have multiplied a fixed t by some little k in here. So this can, of course, also be written in that form, u prime, t prime, k prime, and k varies over k, okay? So I just want to collect all the t's that can happen if I multiply with some random little k on the left-hand side into the set, and I, for the sake of writing it shorter, I write this, the projection onto t of this right coset of k. So I want to determine this, okay? As I said, multiplying by little u on the left and little k on the right, this doesn't matter, so I can just look at a k times t, as I've already done there, and ask what its t prime is going to be. And okay, so how do I do this in SL2? Everybody can do this with their linear algebra knowledge. You can use the Gram-Schmidt procedure to decompose maybe the transpose in an upper triangular matrix on the right and an orthogonal on the left, and then you can read off the t part off of what you get when you compute that, okay? Simply because we forced us to have ones over here. Okay, so this we can do by hand. And what you obtain is the following. These t's, I can encode them as a positive real number, and maybe lambda is bigger than lambda inverse. Then it looks like this. And such a lambda actually stands for now this matrix in T, okay? So every number in this positive array determines a matrix in T. We get for this projection, let me write it like this, the projection of KT is, or corresponds to, let me put it with a correspondence, to the entire interval lambda inverse lambda. So you get everything in the convex hull here. Okay, so one way to convince yourself that this is true is do the computations. Another thing is you can easily observe that lambda inverse will be in here simply by permuting the diagonal entries, okay, and then everything else will be in the interior. Okay, so mathematicians like to generalize things, so SL2 is not good enough for us. If you want to do the computations for SLN though, it gets tedious really quickly. You don't want to do all the terms for arbitrarily large n. So luckily, this was already considered by other people. Or I think was 56, Schwer was involved, 54, but also Thompson in 72. And they proved that for SLN over the reals, arbitrary n, well, you can again write it as u times c times k, that's not the theorem. But for all the t's in capital T, we have that the projection onto the T part of k times T is always the convex hull of Sn times T. Okay, and what do I mean by this? How to read this theorem? Again, similar as we did here, we can encode the matrices in the T over there with an n-1 dimensional vector, recording all the lambdas except for the last one, as we did here. And then we can plot them in an R to the n-1, simply as points, as I've done here. And then one thing to observe is that, well, these two endpoints, they're obtained by a swap of the diagonal entries, which translates to an action of Sn in higher than class. And then again, you, as we did here, you just simply take the convex hull in this R to the n-1 to obtain all the possible T parts. Okay, again, mathematicians like to generalize stuff. SLN is a Lie group, yeah, with a spherical Weyl group Sn.
Can I ask a question?
Yes.
Can you explain why they cared about this particular question?
It had to do with eigenvalues of diagonal matrices and how they could change, but I don't recall in which context they were looking at that. But that's definitely how Schwer and Hahn came to that problem. Yeah, I do know, however, how the next person cared, because he wanted to generalize this to Lie groups, as I just indicated. That's a theorem by Constant from, if I recall correctly, 76. Here you take G, a Lie group, a real Lie group. And again, you obtain for all T and T. So here you want non-compact type, the symmetric space to be of non-compact type. So, and then again, you obtain for all T that the projection is the convex hull. Now Sn replaced by the obvious thing, namely the spherical Weyl group. So I put spherical here because it's a finite group, and we'll see later why I want to emphasize this. Okay, so Constant proved this using geometry, namely the symmetric space associated with the group, which as a set is the same as G mod K. And yeah, these symmetric spaces have been used for a very long time to prove algebraic statements about the Lie groups attached to them, or actually it's the other way around. If you want to prove things about the Lie groups, you can use the symmetric spaces attached to them. And again, another obvious question for how to generalize this is if you do not take a Lie group over the reals, but over some non-archimedian thing, namely or function fields. So what about, write it like this, SLN F, where F is just an example P here, or FT. There's no longer a symmetric space around when you look at these groups. And this is a thing that bothered many people in the 1960s, among others, Bruhat-Tits and François Bruhat, who introduced spaces analogous to symmetric spaces attached exactly to those kinds of groups. And those are the buildings I want to talk about. Okay, so definition. The building is a symmetrically complex together with a system of apartments, which is a system of subcomplexes. I want to record the system as a script A, all its elements, apartments, such that a couple of properties are satisfied. First, I want X to be, sorry, not disjoint, to be the union overall A in A. And as I just said, it's not a disjoint union, very much not so, as we will see in examples in a few minutes. The A's, they correspond to the Weil groups, they're Coxeter complexes. And these Coxeter complexes, you should think of them as being embedded in this big simplicially complex, and there's many of them. So there's really a lot, and the first axiom is...
Sorry, will you tell us what a Coxeter complex is?
Yes, I will, but after I finish this definition. First, I want to let you know what the gluing mechanisms look like of these subspaces we're going to look at. So first axiom you want is that for every pair of species in X, there exists an A in your apartment system such that both of the simplices, which I haven't specified, are in A. And then the second thing is a compatibility thing, which allows you immediately to prove that all of these Coxeter complexes, we'll get to that, are actually of the same type. They belong to the same sort of group. So whenever you have an A prime in your apartment system, both containing a simplex C, then the simplex should be top dimensional. Then there exists an isomorphism from A onto A prime, fixing their entire intersection, including C pointwise.
That's an isomorphism entirely.
No, that's not an isomorphism of X. It's just an isomorphism from A onto A prime. Yeah, that's important here. Okay, Coxeter complexes. So for the sake of this talk, you can think of them as tilings of either spheres or Euclidean spaces obtained by a co-compact action of a reflection group. I'll be a bit more precise. They're associated to Coxeter groups. And a Coxeter group is one of the following form. You have a finite generating set, S1 to Sn, and you ask that your generators are reflections, hence they're elements of order 2. And then you fix pairwise orders. And one can actually prove that these MIJs are actually the order of the product of SI, SJ in this group presentation, which is a non-trivial thing to prove, such that these orders lie between 2 and infinity. And by equal infinity, I simply mean there's no relation for that pair. Okay. Okay, examples. You've seen one, SN. It's one class of examples. And well, the first one you can think of as, well, let's say S3. It's a symmetric group on 3 letters. So it's the symmetries of a triangle generated by reflections. And here are my 2 reflections. And if you do so, you obtain actually 6 elements. And the Coxeter complex will turn out to be a hexagon here corresponding to the vertices of the triangle you started with, plus another class of vertices in a different color, which corresponds to the barycenter of the faces of the triangle. So overall, the Coxeter complex, which I denote by sigma, depends on the pair WS, is a hexagon here. Another example, one up, S4, you would have symmetries of a tetrahedron, permuting the 4 vertices of the tetrahedron. And again, the Coxeter complex is, as a simplicial complex, the barycentric subdivision of the tetrahedron. Now you get 3 colors of vertices, the original 4 ones you started with, the centers of the faces, but then there's also the centers of the edges here. And these 3 colors correspond to the 3 generators you now need to produce this group as a reflection, okay? What we have is a 1-1 correspondence between elements in W and the maximal simplices in this complex sigma. And let me show you one more example. So these are finite groups, obviously. Not all Coxeter groups are finite. There's affine ones acting on some R to the N. And in R squared, for example, if you take, you do it in color, an equilateral triangle and the reflections along its 3 faces, then around every intersection vertex, you get exactly the S3 back we've seen here. But in total, you get a tiling of the plane by equilateral triangles. And again, every triangle in here represents 1 element in an affine Coxeter group, and this is the Coxeter group of type A2 tilde. Do you have questions so far?
So is the Coxeter complex of this then just this tiling of the plane with the?
Yeah, it's just this tiling of the plane. In general, it's the order complex of the coset of special cosets, where you take all the special subgroups generated by subsystems of your generating system S, you order them by reverse inclusion, and the order complex of this thing will give you exactly this, where the maximal simplices are the smallest subgroups generated by the empty set, which then gives you as cosets just element times trivial group. Hence this course. Examples for buildings. The first one, which I won't explain in detail, is that you can take the incidence graph of the Fano plane. And by this, you will obtain a building. The Fano plane, we all seen this, you can view like this. It has 7 vertices and 7 lines, so you will get 2 colors of vertices and lines. which correspond to exactly the two colors we had seen here in S3. So this is, for those who know, this is constructed as subvector spaces of the vector space V to the 3. So we have S3 acting here, and every apartment will look like this. It will be one of the S3 apartments. Every apartment will correspond to a basis generated. You span the lines generated by the three basis elements you have, and then you take the joint spaces to be two-dimensional subspaces. So here would be E1, E2, and then again permuting the basis vectors within a basis just permutes vertices within an apartment. Okay, so apartments correspond to choice of a basis for, let me see, F3. Okay, so F is F2 here for the Palmer plane, but you can obviously do this for other choices of fields. Okay, so apartments, yes.
Is this typical that you can take the incidence graph of some
Yeah,
plane arrangement, or is this special?
not hyperplane arrangement. You need more specific, but geometries, yes. Yeah, okay, let me say it now. The buildings, one can actually prove that in the spherical case and affine case, so there's three cases for the Coxeter groups, finite ones, which are tilings of spheres. There's affine ones, producing tilings of R to the n's, and there's the rest, which is infinite non-affine ones. A lot of them are hyperbolic. The spherical and affine ones, they can be classified, and in higher rank, all of these buildings, despite looking very innocent as simplicial complexes here, they are of what we call algebraic origin. They're always constructed by means of a group scheme over some field, either with or without valuation, and the machinery that goes into this are BN pairs, which have been studied in the 1960s by Iwahori, Matsumoto, but also Tits, Bruhat-Tits, and others. Okay, so there's lots of algebraic machinery in the background, and in higher rank, everything is algebraic in the sense that you can always come up with a group in order to construct this space. Let me comment on affine ones a little bit. So this would be an example for an affine Coxeter complexes. Hence, all these apartments look like copies of the same R to the n. And they're glued together. So this incidence graph here, you can arrange the 14 vertices on one big circle, and then you have diagonals. So this is a gluing of hexagons. Affine buildings will be gluings of this plane here, where the intersection is always bounded by these hyperplanes along which we can reflect. So here is an affine example, drawn it to save me some time beforehand. This is the building associated to SL2 QP, where P equals 2. So the P here takes care of the value of the branching. You will see P+1 edges at every vertex for any given P here. I've done the picture for P equals 2. Again, the choice of a basis corresponds to an apartment. This is this base apartment A here. We now have, again, a while group acting on A, but this is an infinite group now, which is an affine while group. In that situation, we will find two while groups, a finite one, a circuit one, and an affine one. And the affine one is the semi-direct product of the color-preserving translations by a reflection at the origin. And then you can make a lot of sense about a lot of algebraic things in this picture, namely for this decomposition we're looking at, U times T times K. U becomes the stabilizer of a direction at infinity, which is the equivalence class of rays pointing in that direction. T becomes the color-preserving translation in the base apartment, and K corresponds to the stabilizer of a preferred vertex, which I call the origin. Okay, so all these three groups, they're now something geometric, which is encoded by this tree. And then trees have, not only the trees, buildings have many nice features to study them, which will then give us powerful tools to say things about the groups attached to them. Okay, so one of these features I would like to introduce now. It's retractions. And retractions are, well, first of all, they're maps from the entire building onto one preferred apartment. And I take the apartment that corresponds to the maximal torus T I've been looking at lately. So let me put this as a fact / theorem. This goes back to Tits, Bruhat-Tits. Every affine building admits two types of retractions. The distance non-increasing simplicial maps from X onto A, again, such that they have geometric meaning. And I'll put it like this: rho inverse of TK is the same as the U orbit of TK, and R inverse, and here I need a little W0 TK. This is K TK. On the nose, R inverse of a TK will be the I orbit of TK, and this is the evaporic group. If you have never heard of this, it's the stabilizer of the identity simplex. So let's call this C1. You pick your favorite maximal simplex, take its stabilizer in the group you're acting on this building, and the I is just that. Okay, well, this looks familiar, right? So we now found things which help us encode U and K orbits. Now, either you can view this on the Grassmannian, left cosets of K, or you remember that we were saying K is the stabilizer of a vertex in here. So every other vertex in our building of the same color is also a left coset of K by conjugating that stabilizer around to other places. So these here, they're vertices in my building X, okay? And applying with something on the left just gives me orbits of vertices in this picture. So let me do an example here. Here's my TK. Why do I need the W0 here? Well, as I said, I want a left coset by K. If I just look at TK, I don't get that. W0 is the spherically Y group. And one fact is that every affine Y group splits as a semi-direct product of T and a finite one, where T is really the color preserving translations in our base apartment. Okay, and I take that finite group to act on here. So in my little apartment over here, which is one dimensional, I just get one additional vertex. Let me put it little W0 T to the lambda K. And then what do these retractions do? This retraction fixes a direction at infinity, meaning that every line in this tree that faces to that point at infinity, so it comes from here and branches off somewhere, those get permuted by the U action. So taking the U orbit of something produces circles like this, and I can show you exactly where it goes. So TK, if I have to fix this direction at infinity, but I'm allowed to branch off. So it goes here, here, also here. And then I have one up here, which I haven't drawn. I get 8 and so forth. Okay, so it's really a horror cycle around this point at infinity. And this other retraction, R inverse, it's yellow. This one was the blue one. This really fixes this identity simplex and permutes things left and right. Okay, so while applying rho pushes everything in this direction, applying the yellow thing pushes it to the left and right, giving me a circle around the origin. If I apply it to the W0 orbit, I get these, also these, and then these as well. Okay? So they do intersect, which is what I want in order to come back to this question, but they're not the same. Using these retractions, well, I was able to prove in 2009 that G, let me put it like this, with a Bruhat-Tits building. So whenever you have a group such that you can construct such a geometry, and then for all T and T, the same holds. Projection onto T from KT. This is the convex hull of the Y orbit. I need to put a little star here, which means the following. These actions of U and K, they preserve color. So white vertices will be mapped onto white vertices always, black vertices onto black vertices. So I have to take the vertices of the same color. That's why it's the star. Anything in between, I won't be able to reach. All right. So
What does convex hull mean in this context?
yeah, it's really the metric convex hull in this picture. You can make sense of it in terms of dual hyperplanes perpendicular to co-weights rather than co-roots. One can prove that it's the exact same thing as taking the metric convex hull. So if here's your origin, say here is your T to the lambda, and then you really take the spherical Y group orbit of this guy first, which will give you 6 vertices in here. You take the metric convex hull, Euclidean distance, and then you take anything in here, which is also a white vertex. All the COVID lattice elements. More questions?
Could you explain again really fast how you color these vertices?
Yeah, maybe we can do that after the talk. It comes from the, okay, really fast is you do the opposite of the walls you're reflecting on. So if you have a generator here, then this gets color S. If you have a generator T here, then this gets color T, etc. Enjoy the water. Okay. And the whiteboard. Canvas. I haven't mentioned galleries yet. Oh. How do galleries come into play? First, I should tell you what a gallery is.
Can I say a question?
Yeah.
So I think Austin, one of his motivations was the total lattice. Is the total lattice involved in buildings?
Not entirely sure how to answer that question.
Thanks.
Yeah, let's talk about it. Okay, galleries. I promised galleries in my title. A gallery in either one of these Coxeter complexes or in fact in the entire building X is a sequence of simplices of a very specific kind. I like to write grammar for galleries, and I'm allowed to start with any simplex I want. Typically in this situation for the convexity theorem, I would want a vertex here. And then I want a chamber, which is a maximal simplex, in which this vertex is contained. And then I alternate between chambers and codimension 1 bases. So PI is always a codimension 1 phase of CI and the previous one, CI minus 1. So really what I want is a sequence of chambers such that subsequent ones contain at least a common codimension 1 phase. And you're allowed to repeat chambers, okay? So you could start out with multiple times the same chamber. So in this picture, we start at the identity simplex. Then a gallery would be, say, this identity simplex, then this codimension 1 phase, the next simplex, then this phase, and then this simplex. Or we could go in the opposite direction, and then maybe, so here's my Z0, C1, C2, and then I decide to repeat this thing. But in order to repeat it, I also have to record a phase in between, a phase of this now repeated simplex. And the way I draw it is I draw it as if I would bounce off of that codimension 1 simplex here. And then this could be, well, C2 and C3. And then we could end here with C4 and C1, okay? So they look like little paths that get folded on top of each other. So in here, like a minimal one would be this, going from the center of this simplex to the next one, but I could also start here and then branch off and repeat this simplex, or I could go further and then branch off and then keep walking in a different direction, okay? So they look like these wiggly paths in our apartment. So why are they useful? Just take my notes in order to not forget writing something. So fact, these galleries, they help us to keep track of the retractions. So when you apply one of these retractions, either the blue or the yellow one, it's often hard to keep track of where these end vertices go. Okay, but one thing you can observe, it's a little bit easier for the yellow one, is that your distance to the origin is preserved. So these are all 2 edges away from the origin. So what did I do here? So for example, I plugged in a gallery that connects the identity with this simplex right before the vertex I'm interested in, and that would be my little Fn, that last vertex, and my F0 would maybe be the origin. And then I can apply this retraction simultaneously to all of the simplices in that gallery. And this really puts me then up here, or even up here with my gallery. And if I then apply the blue gallery, this will give me one that actually bounces off here, because the blue retraction puts this piece onto that piece. Okay, so they really help to keep track of the retractions. And let me just put it vaguely like this. We can encode these orbits as collections of endpoints of certain galleries that are either folded away, and we call this positively folded from this point at infinity, or folded away from this identity simplex as in the middle, because I'm flattening my left and right with that other retraction. Okay, one can make this more precise, but for now, you just keep it like this. And then this yields what is known as gallery models. And gallery models, they're powerful tools. Combinatorial models and toolkits based on galleries. So you keep track of a collection of galleries, you manipulate them with operators or explicitly by doing geometric operations to study algebraic and representation theoretic objects. Well, then I'm definitely not the first to look at these kind of things. So morally, yeah, this really goes back to Tits and Bruhat-Tits, who encoded these groups with these buildings. But a very prominent example of such a thing is where you don't look at galleries, but at geodesics between points, so paths, and then you have the Middleman path model, which was introduced in the 90s, and it explains finite dimensional representations of connected semi-simple complex algebraic groups. There's Grassmannians, which a little bit later in, what did I write down? 05, used now galleries to explain, among other things, MB cycles, which are the Mirkovic-Vilonen cycles, and polytopes as well. And then skipping a lot, there's work by Lis Milicevic, who's actually supposed to be here, but is sick today, unfortunately. Myself and Anne Thomas from 2019 and 22, where we computed non-emptiness and dimensions of certain affine linearistic varieties. These are varieties attached to the affine flag variety, notoriously complicated to understand, and we use gallery models and geometry of buildings to study them. In order to do that, we needed more general retractions. So I told you that in an affine building, we have two types of retractions, the ones based at infinity and the ones based at a simplex inside your apartment. The ones with the simplex inside an apartment, they actually exist for every building, okay? You just don't have an infinity if you, for example, are in the situation of a circle building. So that other retraction does not make sense. But in fact, in an affine building of rank n, let's see, how do I want to put this? A Bruhat-Tits building. rank n admits n+1 types of so-called chimney retractions attached to simplices in the Bruhat-Tits buildings of its Levy factors. This goes back to a lot of people. Let me put some names. There's Givard, Remy in 26, Kapas, Lekubel in 2011, again Milicevic, myself, and Thomas in 23, where we formalized everything and proved the corresponding connection with orbits of groups. So let me just put it like this. Chimney retractions encode also orbits in affine flag varieties. I do not want to put the formal analog of what's up there, but that can be done. And then this also controls more general double usage intersections. Why am I saying double coset intersection? So this theorem here, that this projection is contained in this convex hull, can be reformulated as follows, namely, you asking that this projection is the convex hull is equivalent to saying UTK intersected KTK is not the empty set, only if and I have to put the prime in the correct place. I think it's here. E prime is in the convex hull of W0. Okay. And these kind of double coset intersections, they can be generalized to things in the affine Grassmannian, whether you replace the K by an Eva-Hore or by Eva-Hores in the parabolic. And let me finish by showing you a picture of a higher dimensional building and examples of these chimneys I've mentioned in the last couple of minutes. So in the middle here, you see a building of type A2 tilde. The base apartment is this horizontal flat over here, which is exact same copy in perspective of the example we've been looking at over there. And then, as I said, lots of other copies of this thing are glued onto it. And they branch off, like I've indicated here. So they might have a half space in common with A, but then the other half space pops up out of the building. And if we are here again over characteristic 2, branching is at valency 3. So at a hyperplane, 2 things come off. Okay, so 2 more half apartments come off and they keep branching. And if you don't look at the usual compactification, but at the Satake compactification in this setting here of buildings, you will see at infinity the little trees we've had over there. These are the SL2 Q2 tree for the Levy factors. For example, for the upper left Levy block, you see inside SL3, which is a copy of SL2. The next one over would be the one for the lower hand block, where you put a 1 in the left upper corner and then the SL2s in the lower right corner. And then the rest is sparsed out versions of that. So all the Levy factors. So they give us a compactification again, and as you know, at infinity, we can retract, for example, with respect to this edge that was the yellow thing over there. Here's the red, first one's yellow. Again, we can retract with respect to things inside the building, which is represented by this triangle here. And we can retract, and here I managed to match the color, with respect to infinities. Namely, there are now equivalence classes of Weil sectors, same as over there, but there they happen to be rays. So you see again the old reflections, yellow and blue, but now you get new ones with respect to these chimneys, and you should think of those as being filters on the half spaces pointing to infinity, or somehow represented by a choice of a parabolic plus a direction. We have to pick out a direction inside the strip to make sure we're retracting with respect to this thing and not the other one on the other side. But these are technical details. So here, this little branching comes from the branching here. The yellow retraction, it's on that side, so everything gets pushed that way. This branching is pushing everything up here that way, and the red one would put everything up here. So you can see there's various effects depending on U1 also goes this way and that way. So depending on, with respect to what you're retracting, it has a different effect on the building you're looking at. And with this, I'd like to thank you for your attention and stay.
Questions?
Can you say something about how you use this combinatorics to get the dimension and not maybe you mentioned this, but yeah.
No, I didn't tell you how I do this. So the non-emptiness can be translated, and this was work by Grassmannians, Kotlitz, and Ruman into a double coset intersection statement. Not this one, but involving ones with Überhoris instead. And then we prove that non-emptiness is equivalent to a certain positively folded Gary to exist. So the affine delinealistic varieties, they come with two parameters, and you can assume that both of them are elements in your Coxeter group or Weil group. And then one of them is the type of the Gary, like the one you start with, folding it positively, and you ask it to land on the other one. So it's the end alcove of the positively folded Gary, or end vertex, or end alcove in that game. And then dimension is the statistics on the Gary. So you're counting folds and crossings of a certain kind. So that was really inspired by the work of Littleman and Gusson Littleman, where also, Gary statistics helped to compute these kind of things. It's very delicate though. So morally, the existence of a Gary gives you the non-emptiness, and a certain statistic on the Gary gives you the dimension.
Any more questions? Well, that doesn't seem to be the case. Thank you.